Okay, thanks. Yeah, let me know if you can't hear me or if there are any technical problems.
No, it's fine. We can hear you fine.
Great, okay. Right, so today, thank you very much for the invitation. I'm a bit sad not to actually be there in person, but I'm happy anyway to be joining and to be able to present some work I've done on the initial condition problem for inflation. Yeah, okay, it works, good. So fortunately, given the talks that we've had so far, I don't really need to motivate the idea of inflation. We know that it solves the horizon and flatness problems and that it predicts a spectrum of scale invariant fluctuations. So really what we're talking about is trying to understand why the CMB looks like it does. And in this talk, I'm going to be potentially a bit attacking inflation. I think that's my job with this topic, is to try and really challenge the idea of inflation and the conceptual questions behind how it can get started. But I don't want to take away from these achievements of inflation. I mean, clearly, inflation is a successful theory and it explains many features really fantastically well. The perturbations in the CMB in particular. So although I won't talk about any of this particularly and about the successes of inflation, I just want to say, okay, I do recognize that they are impressive. And so what I really am going to be talking about is actually what you see in this picture is this very bright white light that's always sort of put over the beginning of the universe in these kind of pictures, that always slightly reminds me of this cartoon. I think you should be explicit here, right? So we kind of put this white light over it as if to say, oh, well, okay, we're sort of blinded by something and we just can't see what's happening there. And, maybe we just shouldn't ask any questions about what happened in that region. And that's exactly what I want to do. I want to ask questions about what did happen there and how could inflation actually come out of this bright light? Is it consistent with the sort of the conditions that we're putting on it? So just to sort of recap and make sure we're all on the same page. So the key point that inflation is supposed to solve is the horizon problem. And the idea being that we see 2 points coming from the last scattering surface on the CMB. And when we naively rewind time in the universe, using the standard FRW cosmology that we have, what we find is that we don't have enough time for these 2 points to have communicated with each other prior to the last scattering surface. So this point can have been in contact with everything in this orange triangle, and that's represented here as this orange circle, but it certainly can't have communicated with this one over here because there just hasn't been enough time since the Big Bang singularity. But we get around that by kind of introducing this period beforehand where the co-moving Hubble radius is shrinking. And that does the job for us because it creates this extra time in which these 2 points kind of come into causal contact. And what we find is that we need a fluid with an equation of state which breaks the strong energy condition. So P over rho, so the pressure of the fluid over the energy density of the fluid that's dominating the universe at that point needs to be greater than -1/3. Well, no, sorry, that's the strong energy condition, and it needs to break that, so it needs to be less than -1/3. So the kind of the story that we all get told when we do our, I don't know, our undergraduate degrees in physics and we do cosmology, we're just kind of told this story where we say, once upon a time, a long, long time ago, there was a scalar field on a hill and it starts to slowly roll down. And so the picture that we have is represented, so I'll show a lot of pictures like this where I have one picture, that's sort of the field space picture, so the field versus the potential energy of the field at that value. And this is the sort of standard slow roll picture where this point rolls down the hill. But then what I want you to very much have in mind is also the physical space, like the picture of the universe. And in this example, it's really boring because the field just has a value of a constant everywhere in space. So this green dot really represents the whole universe. Everything's at the same value. And because of that, we can, in the expressions for the pressure and the energy density, we can get rid of the kinetic terms and the gradient terms. And we're just left with the potential energy dominating these values, which leads to a value of P over rho of -1. And so that obviously fits what we need in order to get the right behavior. And so as inflation proceeds, the value of the field slowly rolls down the hill and ends up in the minimum for reheating. And so it probably oscillates a bit when it gets there, which is another nice feature because it can potentially do the job of reheating the universe. But this is kind of the physical picture that we have in mind when we talk about inflation generally. So what I think the story should be, the more realistic story that we don't talk about so much is, once upon a time, a long, long time ago, there was a fairly complicated set of initial conditions. So that if the whole point of inflation is to take a universe that's very inhomogeneous and make it homogeneous, then we should be starting with something where our field has some fairly random profile, perhaps. And so these terms will not be negligible. So both the phi dot terms and the gradient terms will play a role. And so it's not immediately obvious that this is going to start slowly homogenize and then start slowly rolling down the hill. In addition, something that I've highlighted here is that we also have the metric. So if these fluctuations are really large, then not only will we have the dynamics of the field, but we'll also have the dynamics of the space-time metric. So if they're very large, they're very overdense regions, you're going to have regions that may collapse into black holes or back reaction effects that are going to change the behavior of how the scalar field evolves. And that's potentially dangerous for inflation. So inflation may actually not be able to get started in the first place. So this is basically the initial condition problem for inflation. So I like to see it in terms of this kind of flow chart. So you start here and you say, okay, let's just say that space-time and the field are homogeneous prior to inflation. But okay, then inflation is not needed. So at least for the horizon problem, it's not needed. So you can argue, you still want causal initial conditions, or you still want the primordial spectrum of fluctuations. But for the horizon problem, certainly you kind of don't need it anymore. So then, okay, that leads you to the next one, which said, okay, then they must have been inhomogeneous pre-inflation. But then you reach this question of, can inflation have really got started? And in some cases, you find that for certain models, it cannot have started with even fairly small perturbations in the initial conditions. And so a lot of people have thought about this and then debated it quite a lot. And there seems to be, I think, 3 reactions to this problem. So the first one, which I think is the sort of standard one, is, well, we should only consider, or we should look for inflationary models that are robust to inhomogeneities. Okay, so we should try and find ones that do, in a way, it's a pointer to good models of inflation. Maybe it helps us rule out some models of inflation that aren't so robust to these inhomogeneities. So the second reaction is a bit more controversial. So we should throw away inflation and find a new paradigm that works better. Which, okay, it's good, but then you need to find something that also satisfies, that explains things that we see, like the fluctuations in the CMB, as well as inflation does. And I think the final one is some people will just go back to the start and say, well, maybe the natural exit from whatever quantum state we had at the beginning of the universe was something that was homogeneous. And so maybe we should just, not even be trying to find these models that try to smooth the universe. Maybe we should just accept that that is perhaps some kind of natural state, which we would understand better if we had a theory of quantum gravity. And I think all of these reactions to the problem are fine and are good if we actually are going to think about it, because as long as we're thinking about this problem, it can drive us to new ideas. What we just shouldn't do is just ignore it and treat it as this white light that we can't look at. So having said some models of inflation are robust and some aren't, let me explain that in a bit more detail. So the criteria of robustness can be understood as the slow roll solution being an attractor in the phase space of initial conditions. So in the simple initial case where I just said, okay, everything has a homogeneous value of the field phi at the initial time, it will have some initial time derivative, phi dot, and some initial value. We start here in the phase space. And what you hope is that when you evolve that with the Klein-Gordon equation for a standard minimally coupled scalar field, it will take you into the region of the potential. So this phi value will be somewhere on the inflationary potential, and the value of phi dot will be small so that it's a slow roll, which is what you need for inflation. So this is the idea of robustness, to try and have wherever I start in this phase space, I end up here in this slow roll regime. And then we would say, okay, well, it's natural then that inflation should happen for this model. So an example of this is m squared phi squared inflation, so sort of standard quadratic potential, does have an attractor structure in this phase space where you do tend to end up on these slow roll trajectories. So this kind of convex potential. So that's good. So unfortunately, I think that m squared phi squared inflation is semi-ruled out now by the Planck data. But at least some models do have this structure. And sort of a rough rule of thumb is actually that small field models are not robust and large field models are. So small field models are ones where this distance that the inflaton rolls during inflation is small compared to the Planck mass. Whereas large field models are the opposite. They roll a distance during inflation. This sort of inflationary region is the size of roughly a Planck mass. And that's unfortunate in a way because it's not really what we prefer. So why don't we like that? So firstly, small field models, as you can see from this sort of example that I've given, tend to be concave. So they tend to sort of be like hilltop models that turn over, whereas large field models tend to be convex, like the m squared phi squared potential. And as we saw yesterday in some of the data, the Planck data seems to favor the concave models over the convex models. The second point that's a bit against large field models is these are in theory supposed to be effective models of some higher energy theory. And so they would be expected really to break down at the Planck scale. So to have distances in your effective potential that are of the Planck scale is a bit questionable, or at least it's hard to then embed this in some higher energy effective theory. So although there are some models that are robust, as I say, they tend to be ones which are disfavored for theoretical or observational reasons. So there's a very nice review by Robert, the initial conditions for inflation, which goes through all of the previous work that's been done on this. So there's a lot of work on looking at the sort of the phase space of initial conditions. But all I've talked about so far have really been just looking at sort of phi and phi dot. But obviously the initial condition space is actually potentially much bigger and much richer than that. You don't just have a single value of phi and phi dot. These are actually going to be functions, as I showed, they're going to vary across the initial sort of the initial time slice. And even what time and space are, that's kind of encoded in how we choose the metric. And the metric itself is not necessarily going to be homogeneous. It's also going to be kind of bumpy and potentially in a way that's going to disturb inflation. So this is a very schematic picture, you're going to start at some point, and you're going to again hope to end up in the slow roll regime. But obviously this is a much more complicated system to try and solve, to work out the trajectories in this space, rather than just a couple of directions. So in general, this problem can't be solved in an analytic form. So I guess I should say that you're not completely free of where you choose your points in this space. So there are constraints on the metric depending on the form of the field that you put in. So there's obviously, if you put in a big blob of energy density, then the metric will be curved underneath that blob of energy density. So there are some constraint surfaces that you need to lie on within this space. But in general, this is an infinite space of initial conditions. And so there's also, so we don't usually think of the models as being part of the initial condition phase space. We usually think of, we pick a model and then we think about the phase space in the context of that model. But we have a kind of a strange problem with inflation in that we don't really know the model. And there's some kind of degeneracy in a way between the model space and the initial condition space. So you kind of have to tell me which model you want to test, and then I go away and work out how it works in terms of this phase space.
Katy, just 1 minute. There's one question I think you should face it right now. So Subodh is asking, can warm inflation models embedded in small field models solve the kinetion problem for the small field models?
Sorry, say again?
So I think what she's asking is that if you have warm inflation model embedded in small field models, can that solve this kinetion problems?
So if you have a which inflation model?
Warm. If you go away from the standard cold, if you have warm inflationary scenario.
Oh, I see, right. So I mean, you can always get round, so this is a bit the point I'm making here, I think, is you can always change your inflationary theory to make things work for you. So in a way, your model space is also kind of infinite, right? So you can cook up some nice model that has a feature which kind of gets you through this initial bumpiness and gets you into inflation. So yeah, for sure, you can get around these problems by adapting your model in some sort of nice way. But I guess, yeah, so the sort of big question is, like, how much do you accept in terms of modifications to your model? Like, how unnatural in a way do you want to make your inflationary model before you say, okay, that's a bit too fine-tuned? Does that answer the question?
I think we can discuss it more in the discussion session. So also you have 12 more minutes, so I don't want to interrupt you again. So you can carry on. Yeah.
No worries. Yeah, okay, so I better speed up a bit. So the question is sort of, what's the measure on these spaces? Like how much of this space needs to work before we say, okay, inflation is good? Or if it doesn't work, how much doesn't work before we say, okay, this is just clearly not working? One extreme example is the case of, you could start with a collapsing universe. If you start with a collapsing universe, then for sure you're not going to get inflation. You're going to end at a singularity in a finite time. And in a way you could say, well, how do you know that the universe will start expanding or start contracting? You don't really know, because you don't have a model of the quantum period that inflation emerges from. So in a way, this can motivate you to think about mechanisms to try and get through from contraction to expansion, so a cosmological bounce. So I was going to sort of highlight some work that's been done to look at finite volume effects. But I'll just sort of leave the references and move on in interest of time. So yeah, to recap, we would like the inflationary models to be robust against general initial conditions, both in the metric and the slow roll field. So if we start at a random point in phase space, good models should inflate, even with large deviations. So we are assuming classical gravity and scalar field dynamics to apply at this point, which is quite a strong assumption. But if we do this, it may help us to cut down the space of possibly inflationary models. So how do we do this? So what I do is to study this problem using numerical relativity. So we do broadly what I was saying, we put in the initial conditions for the fields and the metrics, and then we evolve this using the Einstein field equations, and we see whether inflation actually gets started. So that's the broad idea, put it in and basically see if it works. And so obviously you would say to me, well, okay, you've got an infinite possibility of initial conditions. How are you going to test this as a theory? So fortunately, you can make some fairly well justified sort of classes of initial condition that you can then test and say, okay, is the inflationary model robust to this kind of class of perturbation? And so that's what we've been doing in our work, looking at first scalar perturbations. So this is where the field has some profile, but the initial field time derivative is 0. So this is already a bit unnatural because it's sort of frozen at some initial profile. And it leads to scalar type perturbations in the metric. You can also then add, obviously, a non-trivial phi dot, which gives you a non-trivial momentum density in your initial conditions. So this is a very interesting case. The final case is to sort of add tensor-like perturbations. So this is really, these aren't sourced by the field at all. They're really like large gravitational wave type perturbations in the initial metric. So they are also something that could potentially disturb inflation. And so what we've done so far is the first and the last case, broadly because they're the easiest to implement. And we haven't done the vector case yet, although we are working on it. And I think, in a way, this one is the most interesting one because it will cover sort of the most general class of initial conditions. So I just wanted to highlight other works that have been done. So actually work on this goes back to the 1990s with this sort of pioneering paper by Goldwith and Piran. There are also parallel works on bouncing cosmology scenarios, which is really interesting, mainly by Garfinkel and Pretorius earlier on, and have recently been revived by Will Cook and Anna Idris and collaborators. So on the inflationary front, it was really revived quite recently by this paper by Will East, which was a very nice paper showing that in in large field models, inflation was very robust to very large inhomogeneities in the field. And then these papers are the ones that I'm going to focus on because they're the ones I worked on, and so I can give you a bit more detail, which mainly look at how these conditions apply to small field models. So are there ways in which we can get small field models to be more robust? So let me just quickly say something about large field inflation. So for large field inflation, it is really hugely robust. So you can put in really enormous perturbations in the initial field, and you will still get inflation proceeding. So I think the value of the perturbations we were putting in was something like 100 times the energy density, so the VO phi naught of the field, so the typical energy scale of inflation. And even with perturbations, hundreds of times bigger, you would still get inflation proceeding. So what you would see was black holes forming because you're putting very large perturbations in. So what I'm showing here is something that's a bit like a negative Hubble constant. So blue is expanding and red is collapsing, and what you see here is a black hole. So if I run the video, you can see that you get this overdensity that collapses, and so it looks like it kind of just disappears out of the space-time, but that's because in this simulation your space-time is expanding, and so basically what happens is your black hole gets inflated out of the space-time, so it falls below the numerical resolution of the grid and just kind of disappears. So although these black holes would be created during inflation, they would very quickly be diluted. And so they wouldn't necessarily be visible at the end of inflation, and they wouldn't disturb inflation, you see that the majority of the space-time is still expanding. So I think I'll skip over this. So it's quite nice to see that you can actually, you can't form a big enough black hole to actually eat the entire universe. So one of the questions we asked is, could you make large field inflation fail by essentially eating the universe with a giant black hole? And there is actually a maximum mass for the black hole that you can form, because as you increase the amplitude of the scalar fluctuations, if you think about what you're doing, you're increasing the energy density. So you're actually increasing the expansion rate of the universe. So you're increasing h because of essentially the FRW equations. And so things are sort of inflating so fast or expanding so fast initially that you can't actually take as much energy into your black hole as you could with a lower value. So unfortunately, you can't break large field inflation with massive black holes. So small field inflation. This is sort of the picture of what happens in small field inflation. So what you have is, this is the spatial profile of the field, like the pictures I was showing you earlier. You get these oscillations, and then they are basically sort of damped down. So eventually you do go to this point where you see that things are homogeneous. And so at this point, things are inflating. But what you can see is that in the regions in the corners, you're creeping up. So if you look at the potential that's in the bottom left, what's happening is that these points have basically fallen down the hill into the reheating minimum. And we sort of declare this as game over, because when this happens, very quickly the rest of the physical space is dragged down by the gradients into the minimum as well. So the failure mode for small field inflation is very much one point, a single point falling into the minimum, and then, as I say, ending inflation for the rest of the space-time. So what we can ask is, well, how much inflation did we get before that happened? So if we get enough inflation, then that's still okay. It's okay for it to end at some point. But how much inflation do we get? So we get plots like these where we have the amplitude of the scalar perturbations, and then we have the number of e-folds that we get. And what we see is that even for very tiny scalar perturbations, so ones that are 10 to the minus 4 compared to the energy scale of inflation, we actually see that we get less than 10 e-folds. So inflation is really not working at this point. So only for much smaller perturbations do we actually get inflation happening. But this is a bit unfair, because in the cases that we were studying, we were really studying single large horizon-sized modes. And they turn out to be the most dangerous ones for inflation. Whereas adding higher modes, as we did here, n is 2, actually shifts this to the right, meaning it's more robust. You're getting more e-folds for the same amplitude of perturbation. So even when you're actually increasing the energy density of the fluctuations.
Katy, you have 2 more minutes.
Okay, I think I'm okay. I'll be finished. So we also, as I mentioned, studied the impact of tensor perturbations, so perturbations in the metric that are like gravitational waves. And so what we saw is kind of represented here. So the red zones are inflating well, and in the blue zone, inflation, you're not getting that many e-folds of inflation, so inflation is kind of failing. And what you see is that for very small perturbations in the scalar field, you can actually make this really large, and it doesn't make a lot of difference. So the main driver of the behavior is actually the amplitude of the scalar perturbations. And these tensor perturbations, although they do decrease initially the number of e-folds you get, after a certain level, you can actually keep making them bigger, and they don't seem to make that much difference. And you can understand most of this behavior by, as I say, considering the fact that you're worried about failure at a single point. So you're worried about the fact that your potential gradient is pulling your field down the hill, but what's resisting that is basically the gradient pressure, is the fact that the field wants to flatten. So it has a wave-like behavior, so it wants to sort of go down again. And so you can actually make a condition quite easily on the initial conditions, which relates your potential to the amplitude of your fluctuations, saying that you have a balance between these two things. And this gives you a way to look at particular models and say whether they will withstand a certain amount of inhomogeneity in the initial universe. So given the amount of time I've got left, I'll skip over my last slide. So I just want to say that in this work by Yosu Orokoetseya, we looked at applying this to very specific models, like the ones that appear in Planck, and you can rule out a lot of the space of potential inflationary models using these conditions. And I'll just leave my summary there. Thanks.
So, thank you, Katy. So I have one question from Subodh Mishra. So Subodh, if you turn on your mic and you can ask the question yourself. And also, if you have Professor Tereki Suama, so after this, we will have the discussion session. We have a few more questions for Professor Suama.
Okay.
So Subodh, can you hear us?
Hi, yes. Thank you. I wanted to ask, so for the small field models, you talked about when the field rolls down to the minimum, where the gradient actually grows. When we say it rolls down to the minimum, you also mean that it also has a small kinetic term, right?
Yes, that's right.
Both of them. So how probable was it? Like in what fraction of your initial condition space you saw this kind of?
So yeah, so this is a really good question. So as I say, I guess we can put in any amplitude. So I guess our initial conditions were parameterized by this amplitude of the field. So I think that's where I'm saying that below about sort of 10 to the minus 4 in terms of the energy density of those perturbations, this particular small field model that we chose would fail. But all of these statements are very model dependent. So I mean, that's ruling out really an enormous amount of phase space. Everything above that amplitude will fail for this particular model. So I would probably say that model is not very robust. But as I say, one of the key questions is really what is the measure on that phase space? So how likely was it to have those very small perturbations compared to having the very big ones?
Yeah.
So just looking at it naively, you'd say, well, I ruled out a huge amount of phase space. But in a way, you need to tell me, well, how likely were each of those parts of the phase space in the first place in order to be able to say, okay, no, inflation doesn't work in that case.
So, and what was this model? Which model was this?
I think it was hilltop inflation. So I think it was something like 1 minus 5 to the 4 over.
But then you don't have a minimum in a general hilltop, right?
Very good question. Yeah. So in fact, what we did is we always match at the bottom. We always match them to a quadratic potential, so that when we simulate it, it ends smoothly. But you're exactly right. If we just took this naively, it would fall off a cliff and never end. Yeah.
Okay. So we next have question from Professor Ashley Wilkins. So Ashley, if you are with us, you can unmute yourself and directly ask Katy the question.
She says her mic doesn't work. So maybe
okay.
You can ask the
Katy, Ashley's question is, could you clarify a little why failure at one point ensures the inflation fails? Is there not a chance that inflation ejects the trouble point?
Yeah, right. So that's not what we found. It was something we considered as a possibility, and that seems to happen in large field models where you get these points that are collapsing into black holes and then they're just inflated out. But in the small field models, what we saw consistently was that once one point fell down, the rest of the space did stay for some time on the inflationary potential, but within about 1 or 2 e-folds, that would also be pulled down the hill. So you really could say that roughly inflation ended at that point. So you would get a few more e-folds of inflation from the rest of the space, but it wouldn't just, as you say, exactly as you say, it wouldn't eject that point. It would really, that point would really sort of ruin things for everything.
Okay.
I suppose a point I should make is that we use periodic boundary conditions. So we assume that our universe is a torus, and that actually has implications for that question.
Okay, so we have another question from Professor Fabio Finelli. So Fabio, if you are with us and your mic is working, can you ask the question directly?
Okay, can you hear me?
Yeah, you can go on.
Okay, so I have a question about the concave models, which can admit large field values. So you mentioned you have a slide about deep brain. So if you could elaborate more on deep brain, and then my comment.
Thank you. Thank you for giving me the opportunity to show my D-brain side. Since I ran out of time. So yeah, it's exactly right. So this was an interesting case because it is a concave model, but you can actually have a large field concave model. So there was in this case, what we did was we looked at, so N represents how many modes, basically your K, your number of modes within the horizon. So for single modes, which is most dangerous, you rule out a lot of the phase space. So this mu is the mu that appears in the potential here. So as you make your potential more large field, it becomes more robust. So you do have this region where it still works, but you've ruled out a lot of the space compared to, as I say, the Planck results, which are these dashed regions. So the vertical axis is basically how far you put the center of these perturbations up the hill. So if you put it way up the plateau, obviously it's going to be quite robust and you're going to be okay. But as you put it closer to the failure point, it's going to make it less robust. But as I say, this region is kind of impressive in the sense that here you can really make your perturbations as big as you like, and you will always get inflation proceeding with these initial conditions. So
okay.
So
Thanks a lot. My second.
Okay, Fabio, you can go ahead. Sorry.
Yeah, my second comment is that you are considering an incomplete model. So this D-brain, which is similar to what you write, but I'm not sure, cannot go to phi equals 0 in a consistent manner. So you have to cut the potential. Maybe you can also consider potential which can be completed towards the end of inflation.
Yeah, so as I was saying, again, with this model, as with all concave models, we kind of have to match to a quadratic at the bottom, just to allow it to exit smoothly. And that does affect things. That does affect things when you have perturbations that reach the minimum, then they see this concave part of the potential. So in the paper, we do discuss that in a bit more detail, how this affects things. But yeah, ideally you would something like Sriramkumar works nicely. And that was very robust.
Okay, so next we have Joseph Jackson. So Joseph, if you are with us, you can ask the question to Professor Clough directly. And then we have a few more questions for the first speaker, so we have to go through that. So Joseph, if you are with us.
Okay, my question is, we had a talk before about primordial black holes, and you talk about how in the small field case, it can be a large perturbation can collapse to a black hole. Do these two relate? Could this be an explanation for primordial black holes and, for example, quasars and that kind of thing? Have you looked into that as possibilities?
So unfortunately not. Well, I say not. So you'd have to be very lucky because these collapse very much at the beginning of inflation. If you do get sort of 60 e-folds after that, the number of these primordial black holes that you would have at the end of inflation is roughly kind of 1 per sort of Hubble volume, which is very small. So so you wouldn't necessarily see it, and in addition, it's very small, so it would evaporate very quickly. So the actual size of these is kind of microscopic primordial black holes, rather than being the kind of big solar mass type ones that LIGO is seeing, and things like that.
Thank you. That makes sense.
Okay, so Katy, I think you have already said about the Sriramkumar. So one last question before we go to Professor Suama. So Professor Brickman asked you, what is the situation with the Sriramkumar inflation?
So yeah, Sriramkumar inflation is really robust. So if you go to this paper, if I can recommend you go to the paper, there's a discussion specifically on Sriramkumar, and it was one of the models that we found to be robust against large perturbations. So I mean, as I say, you can always find conditions like a collapsing universe where it won't work, you know, and we haven't tested by any means the full range of possible perturbations. You know, we've still got a lot of work to do, but on this simple class of perturbations, it was quite robust. Yeah.
Okay. So,
but what if you change not initial conditions, but topology of your space? What will happen there? Because you see, this is a model where everything is fixed. So it's much easier to test than to test many different potentials.
Yeah, so topology is a really interesting question. So we are assuming a T3 torus, basically, because we have these periodic boundary conditions. And that's quite a strong influence on the results that we see. So I'm definitely interested in looking at different topologies in the future. They just tend to be more difficult to implement numerically. That's the problem with it.
Okay, so Katy, there are a couple of questions from Sharvari. So this will be the last, and then we will go to Professor Suama. So Sharvari, if you are with us, you can directly ask Katy the questions.
Yeah, hello, can you hear me?
Yeah,
yes.
You can go ahead.
I was just wondering, sorry, if you could just sort of elaborate on the tools, because these are presumably very complicated, nonlinear, non-autonomous systems. So you must be looking for the attractors numerically. So what is the time scale? I mean, what are the time scale involved? Because you could have a robust model where it's not yet achieved that the attractor behavior has not yet emerged, and you could still have this dependence on initial, I mean, you can't classify it as a robust model then. So could you just elaborate a little bit more on how you find these attractors?
Right, so I mean, in a way, we're not really, I mean, we're doing a very trivial thing in that we're just taking points in phase space and seeing where they end up. So we're very much not able to sample the whole of the phase space. We're just sort of saying, okay, if I take this combination of initial conditions in the phase space, do I get inflation? And so, of course, I could have picked one that was kind of a bad point, or that didn't show the behavior that's representative of perhaps the rest of the phase space. But in general, what we see is fairly consistent when we sort of move around the phase space in a way that we can make more general statements. But yeah, as I say, you're right. What we're doing is really, as I say, just taking a single point and seeing whether it ends with inflation.
Yeah, but you could, I mean, look at the actual dynamical system and try and say something. Okay, thank you.
Okay, so thanks, Katy. I will come back to you if there are more questions. So Professor Suama, are you with us?
Let me stop.
Yes.
Turkey, you are with us, right? So there are a few questions, you know, from your previous talk. So Shriya, first of all, are you with us? You can ask Professor Suama your question related to the peak theory. Shriya Hurve, are you with us?
Hello, can you hear me?
Yeah, we can hear you. We can ask Professor Suama your question related.
We'll have to go to the slides.
So Professor Suama, if you can share the slides and go to the slide on the peak theory. I think Shriya has a question on that.
Thank you, madam. My question is because of my knowledge about cosmological coincidence problem. Cosmological coincidence problem is because certain initial conditions are least probable that the densities of dark matter and dark energy are comparable as it is today. Since your studies are on initial conditions in the especially the phase space studies. What the that is on initial conditions in early inflation. Are you ambitious to deal with this problem, and do you think you will be able to help it?
Sorry, Katy, we can't hear you. You have to unmute.
Yeah, unmuted. So that's a great question. So I think so far we haven't thought about that. I mean, really what you need to transition from what we're talking about into sort of the standard Lambda CDM cosmology is some kind of model for the reheating process and how you're generating the dark matter and the dark energy. So I think it's not clear how to go between the two without some sort of concrete model of those processes. So it's not something I've thought about, but I guess you could hope that, especially in terms of looking at these kind of inflationary models, maybe it's something that could feed into the kind of the dark understanding dark energy. But no, it's not actually something I've thought about.
Okay. We would like to thank both the speakers. Excellent talks by both the speakers, Professor Sriramkumar and Professor Katy. Thanks for your time.